In the last video, we saw that in the definition of the Hausdorff content, we can require that the sets be closed without losing any generality. So we used this fact in this video to prove that the Hausdorff measures are Borel regular in the following precise sense. So S is arbitrary and X is any metric space and A is any subset of that. Then for any subset A of the metric space, there exists a Borel set B such that A is contained in B and Hausdorff measure of A equals Hausdorff measure of B. So without sacrificing any Hausdorff measure, we can enlarge our set to a Borel set. And this has important consequences in applications, but we won't get into that in this video. The proof will actually show that we can find a more specific type of B. It's more than just being a Borel set, it's an intersection of union of closed sets, as you will see. So, how do we approach this problem? We have to be rigorous. So if HS of A happens to be infinity, then B can be taken to be all of the space X. So definitely Hausdorff measure of B must be bigger than Hausdorff measure of A, so that also will be infinity, and of course X contains A. So in this case, we're done. So suppose that HSA of is finite. By definition, this means HS delta of A is finite for every delta positive. So we want to take particular deltas. We take delta to be equal to 1 over I for an integer, positive integer, and by definition of Hausdorff content, and the fact that we can take closed coverings. That's where we're using the previous video's facts. Go check that video if you haven't. For every I, there exists some covering closed sets such that, so this is a near optimal covering that gives us the 1 over ith Hausdorff content. So this is infimum of stuff, and so that will be less than equal to this particular sum. So I have used I in a different sense. So j equal 1 to infinity, diameter of EI's to power s. That's always true, but this EI being near optimal means that if you add to the infimum just any positive number, you can also always go below that. So for every I natural number, we find a covering by EJs, by closed EJs, so that this holds. So we let BI to be the union of EJs, j from 1 to infinity. So I didn't use extra notation. Of course, these EJs change as we change our I. And then we let B to be intersection of all BI's, I from 1 to infinity. So what we can immediately tell is that B contains A. This because the union of EJs, by being a covering, contains A. That means BI contains A, so the intersection of them also contains A. Now it remains to show that the Hausdorff measure of B is actually equal to the Hausdorff measure of A. So obviously B is a bigger set, we have this part, but then this is limit as I goes to infinity of the Hausdorff contents. That's just by definition of Hausdorff measure and monotonicity of the content in that variable delta. But this one is less than or equal to limit I goes to infinity hs1 over I. Now I enlarge the set, that's why I have less than. And this is less than or equal to the limit I goes to infinity of hs 1 over I a plus 1 over I. And that one converges in limit to hs of A again. So therefore, HSB is less than and at the same time more than HS of B. It has to be equal to it. And that's over. So B is definitely a Borel set, and it contains A, and the measure is equal. So yeah, an amazing fact about Hausdorff measures in general.